keeping things moving. Next up is Jian Liu from NETINT. Jian, welcome.
All right, thanks, Eric. So good afternoon, everyone. I'm Jian Liu from NETINT Technologies. I'm currently in charge of video fundamental technology R&D in NETINT, mainly focusing on video codec design and algorithm for quality optimizations. So here's a brief overview of our company. Our company was founded in 2015. We actually have a few product lines, but since the very beginning of the time, we have been focusing on next generation SSD controller with onboard video transcoders. We are growing very fast recently. Currently, we have more than 100 engineers worldwide. Most of our team members have quite many years of experience in this industry. And majority of them previously worked for some big companies like Qualcomm, Broadcom, PMC, AMD, etc. We are an international company based in Canada with development offices in China. Our headquarters is located in Vancouver, BC, and we have another office in Toronto. We have a development R&D center in Shanghai, and soon our Beijing and Jian offices will be open. Okay, here's a brief introduction of our recent product. As a hardware video processing solution company, we integrate our purposely built ASIC, what we call Codecity, into solutions that are built for cloud data centers. We have just shipped our new generation of VPUs, where VPU stands for Video Processing Unit. And also we give the name Quadra to it. So here you can see we call it Quadra T1, T2, and T4. Our Quadra comes with a family of ASIC-based video transcoders packaged in U.2 NVMe and PCIe AIC form factor. The unique solution is designed so that our customers, mainly on the cloud side, those video operators, they can easily upgrade their x86 or ARM-based data center servers to hardware-based video encoding servers. So regarding the encoding format support, we are able to encode H.264 AVC, H.265 HEVC, and AV1. Meanwhile, we also have embedded decoders. For the decoding capabilities, we added VP9 decoders, where we believe there's a use case for that. The highest resolution we could support for a single chip is 8K and 60 IPS real-time encoding. So in a short word, by using our Quadra solution, we could offer a 10x density improvement over the software encoders and a 20x reduction in energy consumption as compared to CPU-based workflows. It could reduce the operational cost by as much as 40x and the carbon emission by 80x. Okay, so this is our on the inside the red box. This is our Quadra T1 shipped in U.2 form factor, and the Quadra. Then we have a Quadra T2, which doubles the capabilities of encoding, and the T2. So therefore, the T2 is capable of encoding 8 live 4K 60 IPS 10-bit AV1 streams at broadcast quality. Again, we could double the capability again with our T4, which has 4 Codecity G5 ASICs inside. But regarding the video quality, the quality will not be changed. And we'll talk about the video quality later. Meanwhile, I also need to mention, like, we support, Dolby Vision, also have hardware acceleration for video intelligence, data mining, and other any machine learning and AI applications and services, because we have a powerful AI inference engine, also a CPU, a DSP processor, or other hardware chips inside our Quadra. So the addition of 2 deep neural networks engines, each is capable of 18 trillion operations per second. Okay, here's a block diagram for our VPU workflow. Right now, I'm going to use our Quadra as an example. This figure, so on the left side of this figure, we can see that the videos could be generated and transmitted lively through the internet, then decoded using our hardware decoder. And inside this red box, it's actually our host server. And with the decoded YOV, because we have a embedded CPU and AI engine, we can do some basic additions on top of this YOVs, like we can do text overlaying, timestamp, add replacement, and insertion. Also, we could do even more advanced processing, for example, like identify the region of interest, face recognition, motion detection. We could use for privacy masking, deep learning video analytics, and event generation, the event and alarm triggers. Of course, these are just a few examples about what we can do using our CPUs and AI engine. We could definitely do more with these hardware capabilities. Of course, the main focus will still be our video transcoding. So with the previous video processing or without it, we can re-encode the decoded videos by our video encoding engine, and we could using encoding ladder output, which could fit for different frame rate, resolution, bitrate quality, which might be suitable for different viewing devices like TVs, phones, or different network conditions. So we know that H.264 and H.265 has been on the market for many years already. There have been appeared multiple solutions based on different hardware chips, which could do H.264 and H.265 cloud transcoding in a reasonably good qualities. Well, talking about AV1, so we think AV1, we always consider AV1 as a royalty-free codec, which is more efficient than other existing standard-based codecs. The potential of AV1 to bring a tangible benefit for various video-related apps or services is becoming real. Even though the AV1 standard has been finalized for a few years already, and we have witnessed quite a few software-based encoder, either on the cloud or client side, serving for various applications. Matt Frost from Google mentioned before, compression efficiency comes at a cost of computing. The AV1 ecosystem will soon benefit from having an ASIC-based hardware encoding solution available for the data center. So the product we just shipped is the world's first AV1 hardware encoder. So today I'm going to share with you on our AV1 hardware encoder design, performance, and quality. So we believe the AV1 hardware encoder should and could be used for a wide range of applications, including video on demand, video live broadcasting, video conference, VR, AR, cloud gaming, and even possibly other emerging applications. And these applications will need different video quality range, will have a different latency requirement. But if we do want to have add a limit to the current applications or the future applications, I would say these applications do need to have high speed, high quality video compression. That's why for our video quality compression, we're trying to cover a wide range of HD and UHD video content to be compressed. So for the test sequences wise, we have selected more than 20 sequences, 4K 60 IPS, 4K 30 IPS, and 1080p 60 IPS. Some examples are on, the images are on the right side. And we also trying to select some gaming content besides the PCG content. And some are from the standard test sequences. Different videos will have the different characteristics, like fast motion, slow motion, global pan, zoom in and zoom out. This will try the best effort to validate how good or even how bad maybe for the AV1 encoders, different encoders. Meanwhile, as I mentioned before, we always define our video quality to be a broadcast quality. Well, this kind of definition is somewhat vague. So think about when we are trying to view HD, UHD videos, we would like to have a video quality without noticeable artifacts. This is probably a simpler definition of what is broadcast quality. So that will be our video encoder main operational points. So even though we have tested ultra low bitrate, low quality, or ultra high bitrate with visually lossless video qualities, but this time we would like to focus on those broadcasting level video quality. We have been using PSNR, SSR, VMAF. All of these three indices are showing the same trend. For comparison, we select SVT AV1, the software, open source software encoder, which has been widely used. Version is 0.8.6, which should be the latest one. And we use different presets. The larger the number, the faster speed, but the lower the quality. We selected preset 864. And we use the Intel Xeon CPU. It's a 2699 V4. It has 22 physical cores at which each core the CPU is about 2.2 gigahertz. We also insert our our hardware encoders do not need such a powerful CPU settings, but we are trying to use our hardware encoders configurations to be aligned with SVT AV1 to be fair compression. Bit range will be like 8 megabits per second to 120 megabits per second for 4K 60, and for 4K 30 we reduce the bit rate, and you even reduce more for 1080p. But this should be able to cover most of the use cases. Okay, so first let's look at the performance. Let's take a look. As I just mentioned, if we want to get a good quality, we have to use preset 4, but which is slower. So with our 22 powerful Intel cores, we can only achieve 0.3 FPS for 4K 60 encoding, and roughly like 1 FPS for 1080p. Of course, with the faster the speed, with the higher the number of the preset, but the quality will drop, and we're going to take a look at the quality in the later slides. And also, these numbers is like it's like 0.341, and we just pick a one sequence for that, because for hardware encoders, they use a lot of fast algorithm, and actually we do see the encoding speed fluctuate a lot for different sequences and even different shots. Well, if we put 10 of our Quadra T1 VPUs on top of Dell servers, we could achieve, for 1080p, we could achieve almost 10K IPS, and 4K, for 4K, it's about a quarter of that. It's we could achieve 2,400 IPS, and these encoding speed will always remain as a constant. Okay, now it's time to talk about the BD rate. We use VMAF, which we believe will be closer to the human visual qualities. So look at these different curves. On the top of these curves will be our Quadra AV1. And then we have different curves for different presets. As I mentioned before, the higher the speed, the lower the quality. In average, we could achieve 24% bitrate saving compared with SVT AV1 preset 8, roughly 15% over preset 6, and 6.7% over preset 4. And the maximum gain is about more than 50%. Okay, now here, let's take a look of the visual quality. Yeah, we prove that, we show that VMAF, on VMAF indexes, we are better. And now, so for this is a screenshot from SVT AV1 for 4K video. And then we take a look of this one for our Quadra. It may be slightly difficult for viewing in this webinar, but if we are going back and forth over these two screenshots, it can be easily seen that a lot of details are washed out. More obvious region is those electric poles on the bridge. Almost everything is washed out for SVT AV1, but we still keep all the details for using our Quadra AV1. Okay, another example is for using another gaming content, Witcher 3. It's encoded as 1080p 60 fps. Yeah, so again, the savings will be, the savings numbers will be the same as before because our average is doing across the 4K and the 1080p sequences. And for this specific sequences, roughly we can achieve more than 20% of the gain. And the VMAF number ranges from 75 to 96, 98, which covers which is a good coverage of most operation points human beings would like to view the video content. Okay, here's another example using for a screenshot. This is the SVT AV1 screenshot, and this is our Quadra numbers. This is quite obvious if we probably we don't even have to go back and forth. Just see like the details are gone, and I probably will not call this as a broadcast quality for SVT because it's hard to tell what are those objects are. And here, like we see a lot of details about those grasses and the objects. Okay, so thanks everybody. So we have completed our first round of bring up our Quadra hardware with some quality optimization algorithms, which include rate control, look ahead, AQ mode, etc. But we do believe there's still plenty of room for future improvement. Since the product we are going to ship is a video hardware solution based on our VPU, we are not limited ourselves to be, just the video encoding use our video transcoder. For the video encoding side, we still have not fully utilized our hardware for capabilities, enabling the functionalities like object detection, classifications, segmentations, ROIs, or per scene, per shot encoding, or like even content adaptive rate control, something like that. There could be a lot to be done using the whole hardware solution. And also, we don't think hardware and the software encoders are totally different. Starting from our design period, we designed our hardware encoder considering a lot of techniques from the software encoders. While some of them might be a good fit, and some of them might need to be modified a lot. Again, but we do believe our hardware encoders have a lot of room to be improved. Okay, thank you for taking the time to listen to our presentation. We would like to give you a closer look at what our products can do in our video operations, feel free to visit our website or send an email to info@netint.ca. Thank you.